Saturn's rings are one of the most recognizable structures in the entire solar system. They're bright, they're sprawling, and honestly, they look like they've been there forever, like some kind of cosmic fixture that's just always existed. For centuries, that's exactly what scientists assumed too. The rings, they figured, formed billions of years ago, right alongside the planet itself, born in that same swirling cloud of gas and dust that eventually became Saturn. But here's the thing about science. Sometimes your best assumptions get completely upended by new data, and that's exactly what happened here. Data from the Cassini spacecraft revealed something that stunned researchers. Saturn's rings are young. Not young in a geological handwave kind of way, but genuinely, shockingly young, no more than a few 100 million years old. Think about that for a second. When these rings formed, dinosaurs were still walking around on Earth. That's not ancient history on a cosmic scale, that's practically yesterday. It's like discovering that the pyramids were actually built last week. But that jaw-dropping discovery was really just the opening act. It left scientists asking a much bigger question. If the rings are this young, what else in the Saturn system might be tangled up in the same story? Is there a whole hidden chapter of Saturn's recent history that we've been missing entirely? Then, in February of 2026, a new study finally gave us an answer, and it's a wild one. We're talking about a cataclysmic chain of events with consequences that rippled across the entire system, all of it happening in what amounts to the cosmic equivalent of a blink of an eye. And driving this whole disaster? None other than Saturn's largest moon, Titan. So let's get to the bottom of Saturn's biggest mystery together. We're going to dig into the gravitational dance happening between this gas giant, its rings, and its enormous family of moons, and we'll see how their deeply intertwined relationship set off a trail of destruction that reshaped the entire neighborhood. Let's rewind the clock, way back, to 1610. That's when Galileo Galilei turned his telescope toward Saturn, becoming the very first person in history to do so. And what he saw left him completely baffled. It looked, to his eyes, like the planet was sandwiched between two enormous moons, one on either side. Strange enough on its own. But then, 2 years later, he looked again, and those moons had simply vanished. Gone, like they'd never been there. And then, another 2 years after that, they reappeared. Except now, Galileo described them not as moons, but as something more like arms, or handles, sticking out from the planet. What Galileo was actually witnessing, through his groundbreaking but by modern standards incredibly crude telescope, was our shifting perspective of Saturn's rings. Here's why that happens. Saturn is tilted at 27 degrees relative to its orbit. As the gas giant makes its long journey around the Sun, that tilt means the rings angle toward Earth for a while, and then swing away from us again. When the rings appeared to vanish for Galileo, he was actually just viewing them edge-on, so thin from that angle that they seemed to disappear entirely. Imagine looking at a sheet of paper straight from the side. It basically vanishes into a line. That's essentially what was happening with the rings. It took almost 50 years for telescope technology to improve enough for astronomers to finally figure out what was really going on. In 1659, Christian Huygens deduced that those mysterious arms Galileo had puzzled over were, in fact, a ring encircling the planet. And Huygens didn't stop there. He was also the first person to identify Titan, Saturn's largest moon, the very same moon that, as we'll see, plays a starring role in this whole story. As telescopes kept getting sharper, our picture of the Saturn system kept getting more complex and more fascinating. The French-Italian astronomer Jean-Dominique Cassini soon discovered 4 more major moons: Iapetus, Rhea, Tethys, and Dione. Then, in 1675, he became the first person to spot a gap within Saturn's rings, a division that today bears his name, the Cassini division. The next wave of breakthroughs came in the 19th century. One key figure was James Edward Keeler, who demonstrated that the rings couldn't possibly be solid, uniform sheets, the way they might appear from a distance. Instead, they were made up of countless individual particles, each one independently orbiting Saturn like its own tiny satellite. Picture a highway packed with millions of individual cars, all moving in the same general direction, but each one doing its own thing. That's a lot closer to the truth than picturing the rings as some smooth, solid disk. But it wasn't until the late 1970s that we really began to grasp the full intricacy and beauty of this system. The Pioneer 11 mission and then the Voyager probes transformed our understanding dramatically. Each new mission brought sharper resolution and revealed details nobody had seen before. By the time Voyager 2 flew past Saturn in August of 1981, it showed us for the first time that what we called the A ring, B ring, and C ring were themselves each made up of millions of smaller ringlets. It's a bit like zooming in to what looks like a single brushstroke in a painting and discovering it's actually composed of thousands of individual, finer strokes. And then came Cassini, the spacecraft, not the astronomer. Orbiting Saturn for more than a decade, it threaded its way through the gaps between the rings, skimmed along their edges, and for its grand finale, it plunged straight through the narrow space between the planet itself and the innermost D ring. The data this mission beamed back to Earth completely revolutionized what we know about the Saturn system. It didn't just paint an extraordinarily detailed picture, it told a story nobody expected to hear. Here's a mind-bending fact about the rings. They are astonishingly thin. We're talking somewhere between 10 meters and 1 kilometer thick. And yet, despite that razor-thin profile, they extend outward as far as 282,000 kilometers from the planet. If you want a sense of scale, imagine a sheet of paper the size of a football field, but so thin you could barely see its edge. That's roughly the proportions we're dealing with here. The rings are named alphabetically, in the order they were discovered, rather than their actual position out from the planet, which admittedly makes for a slightly confusing naming system. Working outward, we've got the D ring, the C ring, the B ring, the A ring, the F ring, the G ring, and the E ring. And then, way out beyond all of those, there's one final, extremely faint ring called the Phoebe ring, named after and orbiting near the moon of the same name. So how do all these ring particles stay so neatly organized instead of just drifting apart or spiraling into chaos? The answer lies with what astronomers call shepherd moons. Small moons like Pan, Daphnis, and Prometheus actually sit within the ring system itself, gravitationally nudging particles back into line, kind of like sheepdogs keeping a flock together. Meanwhile, Pandora, Janus, and Epimetheus orbit just beyond the outer F ring, performing a similar job from the outside. And then there's Mimas, discovered by William Herschel back in 1789, which orbits even further out, but somehow exerts an outsized level of gravitational control over the rings despite the distance. By the end of the Cassini mission, the known moon count around Saturn stood at 62. That's already an impressive number, but the discoveries didn't stop there. Thanks to advancements in ground-based telescopes and more recent surveys, the latest moon count has climbed to a staggering 292, and that number is still climbing. That's more moons than any other planet in our entire solar system, by a wide margin. And as a collection, these moons are extraordinarily diverse. There are large, regular moons that orbit close to Saturn, all roughly in the same general plane as the rings themselves, moving in an orderly, predictable fashion. Then there's a whole separate population of irregular moons, much smaller, much more distant, and following wildly eccentric, tilted orbits that suggest a much messier history, possibly moons that were captured from elsewhere rather than formed alongside Saturn. And then, just to add another layer of weirdness, there are tiny ring moons shaped almost like ravioli, little dumpling-shaped worlds, formed as dust particles from the rings themselves gradually accumulate around their equators over time. So when you step back and look at the whole picture, the Saturnian system is far stranger and far more dynamic than Galileo could ever have imagined back when he thought the planet simply had handles sticking out from its sides. Cassini's detailed measurements of the rings also revealed exactly what they're made of, and the answer is striking: 99.8% water ice. The particle sizes within the rings range enormously too, from grains smaller than a piece of sand, all the way up to chunks as big as a mountain. It's actually that ice that explains why the rings appear so brilliantly bright, even when viewed from Earth using nothing more than early Galilean-style telescopes. Ice crystals are highly reflective, bouncing sunlight back toward us far more efficiently than rock or dust ever could, which is part of why Saturn's rings put on such a dazzling show even across hundreds of millions of kilometers of empty space. Cassini's data also allowed scientists to finally calculate the total mass of the rings, and it comes out to around 16 quadrillion tons. That sounds like an almost incomprehensibly huge number, and it is, but here's the twist. That entire mass is still less than 0.02% of the mass of our own moon. So despite spanning hundreds of thousands of kilometers and containing enough ice to boggle the mind, the rings are, in the grand cosmic scheme of things, remarkably lightweight. Combining these two observations led to a scientific bombshell of a question, and in turn, a genuine discovery. Here's the puzzle. Over time, tiny micrometeorite impacts and drifting space dust slowly pollute water ice, darkening it bit by bit, the same way dust settles on a windshield and dulls the shine. So if that's true, why on earth were Saturn's rings still so bright and clean? Scientists realized they could actually use the total mass of the rings to work backwards and figure out how much contaminating dust would be needed to dirty them up to the degree we'd expect, and from that, calculate how long the darkening process would take. The math pointed to something startling. The low mass of the rings implies they likely formed somewhere between 10 million and 100 million years ago. Now stop and think about that for a second. That is an absolute blink of an eye when you compare it to the 4.6 billion year history of our solar system. It's vastly different from what scientists had assumed for decades. Up until this point, plenty of researchers believed the rings had simply always been there, formed right alongside the planet itself, as some sort of leftover birthday decoration from Saturn's creation. But the new evidence flipped that assumption on its head. Dinosaurs, believe it or not, had already been stomping around on Earth for roughly 150 million years before Saturn's rings are even thought to have come into existence. So the real mystery becomes, how did these rings actually get there? This riddle was first tackled way back in 1849 by a scientist named Edouard Roche, who was trying to understand why rings only ever seem to show up around the giant planets. His idea centered on tidal forces, the very same kind of gravitational pull that causes ocean tides here on Earth, just scaled up to a cosmic level. He proposed that between a moon and its host planet, these tidal forces can become so overwhelming that they actually overpower the gravity holding the moon together as a single body. Picture a moon drifting a little too close to its planet. At a certain point, the planet's gravity would start pulling harder on the near side of the moon than the far side, essentially stretching it until it can't hold itself together anymore. It gets ripped apart, and its shredded remains spread out along its original orbital path, eventually smoothing into a ring. Roche calculated a minimum safe distance for this, roughly 2.5 times the planet's own radius measured from its center. This boundary is now famously known as the Roche limit. For Saturn specifically, that distance works out to about 87,000 kilometers, and remarkably, it lines up almost exactly with the location of the ring known as the F ring. As data from the Cassini spacecraft piled up, it became increasingly clear that something truly catastrophic had happened within the Saturn system, and it happened long after the planet itself had already formed. Now let's talk about a doomed little moon nicknamed Chrysalis. Back in 2022, a team at the Massachusetts Institute of Technology proposed a bold hypothesis: that the rings formed after the violent destruction of an extra moon that used to orbit somewhere between Iapetus and Titan, two of Saturn's other moons. They gave this hypothetical lost moon the name Chrysalis. Their theory suggested that Chrysalis's orbit got knocked off course by the gravitational influence of Titan, gradually nudging it closer and closer to Saturn until it strayed too near. As it crept inward, it was ultimately torn apart, and the debris scattered out to form the rings we admire today. However, when this exact scenario was later modeled by researchers at the Search for Extraterrestrial Intelligence Institute, whose findings were published in February of 2026, the results told a different story. It turned out to be far more likely that Chrysalis would have simply slammed straight into Titan rather than being gently pushed towards Saturn to be destroyed there. In that case, most of the wreckage from the collision would have either been swallowed up by Titan's gravity or flung out of the system entirely, lost to space. That kind of outcome simply wouldn't leave enough material behind to form rings. The team, led by astrophysicist Matija Ćuk, noticed something else strange while running these Chrysalis simulations. Hyperion, a small, oddly shaped moon that constantly tumbles chaotically as it orbits, kept vanishing entirely in most versions of the simulated upheaval. It just wasn't there anymore in the aftermath. But here's the thing, we can look up at Saturn right now and see that Hyperion is still very much present. And on top of that, we know its orbit is locked in a specific rhythmic relationship with Titan. The light bulb moment for Ćuk was realizing that this Hyperion-Titan relationship appears to be relatively young, and it dates back to roughly the same period when Chrysalis supposedly disappeared. That was the key insight. Hyperion wasn't just some leftover survivor that happened to stick around through a shifting, chaotic system. Hyperion was actually a direct product, a result, of whatever violent event had occurred. So Ćuk and his collaborators decided to widen their lens and look at the entire Saturn system together, rather than examining each piece of evidence in isolation to figure out how the rings might have truly formed. This meant factoring in Saturn's axial tilt, that 27-degree lean I mentioned earlier, alongside detailed observations of all its many moons. By treating the whole system as an interconnected web rather than a collection of separate puzzles, they were able to run simulations tracking how events might have unfolded over hundreds of millions of years. Their conclusion was striking. Titan likely did collide with an additional moon, but not the modest Chrysalis. This one was about 4 times more massive. They dubbed it proto-Hyperion, since it was this body that eventually had to produce Hyperion as we see it now. Titan itself was quite different back then too. It was smaller, and it traveled along a much more circular orbit than the one it follows today. Across their simulations, a collision between proto-Hyperion and proto-Titan occurred in 42 out of 60 separate runs. And in the simulation runs where no collision happened, either proto-Hyperion or the moon Iapetus ended up getting completely flung out of the system altogether. The team proposes this cataclysmic collision took place roughly 400 million years ago, and that it set off a chain reaction of events that neatly explains many of the observations we make about the Saturn system today. So what actually went down? The researchers traced the chain of evidence back to a moment when Saturn slipped out of a spin-orbit resonance it had been sharing with the other planets in our solar system. Resonance, in simple terms, is when 2 orbiting bodies fall into a repeating rhythmic pattern, meeting up again and again in the same relative configuration. Over time, these repeated encounters produce tiny gravitational tugs that accumulate, amplifying their influence on one another far beyond what a single, one-off encounter could ever achieve. Think of it like pushing a kid on a swing at exactly the right moment every single time. Even a gentle push, timed perfectly and repeated over and over, builds up into a massive swinging motion. In Saturn's case, that small shift in resonance was enough to destabilize proto-Hyperion, knocking it into a 2-to-1 resonance with proto-Titan, which happens to be the strongest, most powerful type of resonance that exists. That means for every single orbit proto-Titan completed around Saturn, proto-Hyperion completed 2 full orbits. This mismatch caused proto-Hyperion to start spiraling inward rapidly, and it wasn't a gentle drift either. This inward spiral put it on a direct collision course with proto-Titan, and along the way, it also yanked on the orbit of Iapetus, shoving that moon into a dramatically tilted orbital path that persists to this day. Eventually, the paths of these 2 doomed proto-moons crossed, and all hell broke loose. Now, about the Titan and Hyperion we actually observe today. The Titan we know is larger than the planet Mercury, and stands as Saturn's biggest moon by far. When the Cassini spacecraft flew past and delivered its cleverly named companion, the Huygens probe, down to Titan's surface, scientists discovered the moon was wrapped in a thick, nitrogen-rich haze. On Titan, methane clouds actually rained down from the sky, forming flowing rivers of liquid methane across its landscape. Its surface geology also turned out to be surprisingly young, with far fewer impact craters than expected, suggesting the surface had been resurfaced relatively recently in its history. In Cook's proposed scenario, when proto-Titan violently collided with proto-Hyperion, huge portions of Titan's surface were completely resurfaced in the process, smoothing over ancient craters and essentially giving the Moon the cosmic equivalent of a dramatic facelift. A large chunk of proto-Hyperion ended up merging directly into Titan during the impact, but not all of it was absorbed. Some of the leftover fragments drifted back together afterward and reaccreted, gradually reforming into the Hyperion we observe orbiting Saturn today. What's remarkable is that this outcome, generated purely from simulations, lines up beautifully with real observations. Most strikingly, Hyperion appears to be only about 400 to 500 million years old, matching the timeline almost perfectly. Its irregular, lumpy shape and unusually low density are exactly what you'd expect from a body that formed out of loosely bound leftover debris rather than a single solid formation process. Its chaotic, unpredictable tumbling rotation is simply a leftover echo of the sheer momentum unleashed during that ancient collision. And not long after it was born from that wreckage, Hyperion was captured by Titan's gravity, and the two bodies remain locked together today in a 4-to-3 orbital resonance. As for Titan itself, the sheer force of that ancient collision shoved it into a highly elliptical orbit. This was a process that had actually already begun the moment Titan locked into resonance with proto-Hyperion, and it only sped up once the two worlds actually smashed together. Just like our own Moon is slowly drifting away from Earth thanks to tidal forces, Titan has been doing the same thing with Saturn, creeping outward bit by bit over billions of years. But here's the twist that really got scientists scratching their heads. Data from the Cassini spacecraft showed that Titan's outward journey is happening way faster than anyone predicted, moving away at a rate of roughly 11 centimeters every year. That's a strange number to explain with normal tidal drift alone, but a massive collision, exactly the kind modeled by researcher Ćuk, accounts for that extra speed perfectly. And the ripple effects of this newly supersized Titan don't stop there. As its orbit changed shape and expanded, it swept through the entire Saturnian system like a wrecking ball, causing gravitational chaos that reached all the way to Saturn itself. As we've been exploring throughout this story, resonances between objects are incredibly important in space, and they don't just happen when orbits line up with each other. They can also create a link between the orbit of one object and the actual spin of another. Here's something worth remembering. Planets are not perfect spheres. The gravitational influence of the Sun, along with their moons, squashes them slightly into what scientists call oblate spheroids, basically slightly flattened balls. This flattening also causes planets to wobble as they spin on their axis, kind of like a child's spinning top losing its balance ever so slightly. Scientists call this wobble precession. Following the big collision, Titan's rapidly growing orbit started messing with Saturn's precession, making the planet wobble faster and faster. This wobbling eventually pushed Saturn's axial spin into resonance with Neptune's orbit of all things. And here's the kicker. The only way this newly formed lock between Saturn and Neptune could actually be maintained, as Titan kept pulling farther and farther away, was for Saturn itself to tilt over onto its side. Because of how giant planets typically form, scientists expect them to have close to zero axial tilt. So Saturn's 27-degree tilt has puzzled astronomers for a long time. The scenario modeled by the team from the Search for Extraterrestrial Intelligence Institute is genuinely one of the most convincing explanations we've had so far for why Saturn leans the way it does. For roughly 200 million years after all this drama, the Saturnian system actually settled down and stabilized. But Titan's relentless outward drift never stopped, and it wasn't long before it caused yet another round of destruction. About 100 million years ago, Titan's orbit became locked into a resonance with one of two inner moons, a 4-to-1 relationship. This gravitational relationship tilted Titan and also shifted the orbits of that inner pair of moons, eventually causing them to collide with each other. The force of that crash, combined with Saturn's powerful tidal pull, tore those inner moons apart completely, scattering enormous amounts of debris across the system. Over time, some of that material clumped back together to form new moons. Some of it was lost to space entirely, and the rest spread out into the thin, glittering disk of material we now recognize as Saturn's iconic rings. That is the story of how the rings came to exist, and it's also why, in cosmic terms, they're actually surprisingly young. And so, as this whole story comes full circle, let's take a step back and look at everything we've covered. The tilted orbit of Iapetus, the strange age and unusual shape of Hyperion, Titan's surprisingly thick atmosphere and youthful surface, its steadily expanding elliptical orbit, Saturn's dramatic tilt and the way it wobbles on its axis, and of course, those absolutely stunning rings. All of it is part of the very same violent story, and all of it was driven by Titan. This model is the very first attempt to weave together so many strange and previously unexplained observations about Saturn into one single, unified scenario. It's a bold idea, and the big question now is whether it can actually be confirmed through further observation and study. Thankfully, we won't have to wait too long to find out, because a brand new mission to the Saturnian system is already underway. The National Aeronautics and Space Administration's Dragonfly mission is planning to send a nuclear-powered, car-sized rotorcraft directly to Titan's surface. This incredible machine will actually be able to fly and land on Titan multiple times, collecting and analyzing samples from many different locations across the moon. Packed with an impressive suite of onboard instruments designed to test Titan's surface chemistry and its atmospheric makeup, this mission has real potential to uncover evidence of historical resurfacing events on the moon. It's scheduled to launch in the year 2028, and it's expected to actually arrive at Titan in late 2034. Ćuk and his co-authors actually end their astonishing scientific paper with a nod toward this very future mission. They point out that even if the specific sequence of events they've laid out isn't confirmed exactly as described, they believe their work can still help frame entirely new hypotheses about how Saturn's incredibly complex satellite system evolved over time. And to me, that really underlines something absolutely central to how science works. None of the underlying physics in this remarkable study is actually new. Resonance, precession, and tidal forces are all extremely well understood concepts that scientists have studied for a very long time. But what this research team has managed to do is show us just how elegantly and beautifully interconnected all these processes can be when you put them together. As for Saturn's rings themselves, the Cassini spacecraft's final act before it plunged into the planet was to dive repeatedly through the narrow gap between Saturn's clouds and its innermost rings. These daring observations revealed that the rings are constantly changing, far from being some static, unchanging feature. Individual particles are constantly jostling one another, and a significant amount of material is actually falling into Saturn's atmosphere, forming a steady rain of ice that adds up to as much as 40 tons every single second. This constant, ongoing loss of material actually suggests that the rings might only last for another few 100 million years before they're gone entirely. The Saturnian system has earned itself the nickname of a dynamicist's paradise, and its intricately interconnected evolution is still playing out even today. It really makes you wonder what this system might look like another 100 million years from now. As it turns out, we're actually incredibly lucky to exist at just the right moment in cosmic history to witness Saturn's magnificent rings at all.